The Electronic Intelligence Subsystem of the Integrated Operational Intelligence System, IOIS, provides an effective means of collecting electronic clues from the atmosphere and, with the help of automatic electronic equipment, of interpreting those clues. It is thus possible to obtain highly useful intelligence of the enemy's radar installations and firepower, what they are, and where they are located. The airborne equipment is capable of detecting virtually all pulse emitters within range of the aircraft. It measures the electronic characteristics and direction of arrival of each signal and records this data in digital form on magnetic tape. The tape is removed for processing. The processing is carried out in the Electronic Data Processing Area, EDP, of the IOIC. The equipment here translates the signals recorded on the tape into alphanumeric form and plots the emitters accurately on a chart of the area reconnoitered. It also provides a hard copy printout of the data. The plot and printout are displayed at the electronic evaluator station in the multi-sensor interpretation area. With the information the system automatically supplies about each plot point, the electronic evaluator is able to identify the type of emitter represented. In addition, the emitter plot thus obtained may be directly correlated with photographic intelligence. With this correlation, it is possible to combine electronic information about emitters with a visual presentation of their locations. Thus confirmed, the information becomes an extremely valuable item of reportable intelligence. The electronic subsystem of the IOIS is a new concept, particularly that part of it that does its work in the aircraft, the up system, as we call it. Everybody has some idea of the photographic principle and how a picture of the scene below gets on the film carried in the aircraft. But what is the means that puts the electronic equivalent of an image on magnetic tape? And how does the signal get from the tape into usable form back in IOIC? In this film, we shall examine the answers to these questions. We shall also trace the role played by the electronic evaluator before, during, and upon completion of a reconnaissance mission. During the planning phase of a mission, the electronic evaluator works closely with the other mission planners. At the outset, he asks the computer to provide him with the electronic order of battle for the area to be reconnoitered, for example, the island of Cuba. On instructions from the computer, a man in EDP mounts the appropriate order of battle tape. On instructions from the electronic evaluator station, the computer reads the tape and provides an automatic plot of all known emitters on the island. The electronic evaluator studies the plot. He analyzes it with the proposed reconnaissance mission in mind. His advice is important in the mission planning. He reports on the types of emitters and their range and indicates the probable zones of increasing danger for the reconnaissance aircraft. The outer zone, in which the aircraft can avoid detection, but will not itself be within detecting range of all emitters. The intermediate zone, in which the aircraft can detect all emitters, but can itself be detected. And the inner zone, in which the aircraft will be within range of surface-to-air missiles. Based on his analysis of enemy radar-controlled firepower, he recommends a line of approach for the reconnaissance aircraft and a flight path most likely to minimize exposure to enemy firepower. In addition to this role in the planning, The electronic evaluator also recommends when the pilot should energize his defensive ECM equipment so as to deceive the enemy fire control radar. He also suggests items the mission should seek to photograph. For example, he may have an emitter suspense site, as an unconfirmed site is called, at a point from which a previous flight received an emission. Now he requests that photo intelligence be sought to help confirm the site. At the aircraft, the magnetic tape is installed. As is the case with photographic film, the tape will have recorded on it the date, detachment, squadron, sortie, and the time of each emitter intercept. To accomplish this, the Signal Data Converter Group provides for the fixed data: date, detachment, sortie, and so on. Real-time recording is provided for by setting the digital data clock, which assures that all sensors, electronic and photographic, record the same time in hours, minutes, and seconds. This is usually Zulu time. While the mission is underway, the electronic evaluator has work to do getting ready for its return. In the light of the mission directives, he has to decide what information he wants the computer to provide him with. In other words, what program he should prepare to use. He asks himself, do I want a plot of all the emitters on the tape? If so, the general processing program should be used. Or he may ask, do I want a plot of the emitters in the Isle of Pines area only? Such a plot is obtained by employing the Area Activity Program. Or the circumstances may be such that the electronic evaluator is concerned only with an area, say, within a 20-mile radius of Santa Clara. He can receive a plot of all the emitters within a given radius by selecting the Priority Point program. Instead of geographic areas, the evaluator may be more concerned with types of emitters. For example, he may want a plot of all the fire control radars on the tape. In that event, he uses the Emitter Activity Program. Let's assume then that the mission plan and the directives from higher authority indicate a requirement for a plot of the radars on the Isle of Pines. The EE calls for the Area Activity Program. He also selects the outputs he desires: teletypewriter and plotter. He may also select the paper tape option so that later the information obtained can be transmitted readily to other ships and ELIN centers using standard communication equipment. Now let's consider how an emitted pulse gets on the airborne tape. The airborne passive ECM system consists of 12 bands of scanning receivers. The bands cover the frequency range from 30 to 14,150 megacycles and are scanned every 15.5 seconds synchronously. Each antenna assembly receives the pulses from those emitters that operate within its designed frequency coverage. This system is capable of analyzing a pulse and recording its characteristics on the magnetic tape in digital form, along with flight data and other related useful information. In general, this is what happens. When the appropriate antenna receives the signal, it sends directional and frequency information to the receiver. The receiver forwards the information to digitizing equipment. For each emitter pulse received, this equipment puts out signals in the form of binary bits describing the pulse, and these bits are put on the tape as the ECM word. Flight data from computers aboard the aircraft is also fed into the equipment, along with items of fixed data. This information is put on the tape in an orderly way so that the emitter signal can be related to the position and space of the aircraft at the instant the signal was received. Now we'll trace in detail how a single pulse from an enemy emitter is put on tape by the up system. The system's antennas give an 84-degree coverage on either side of the aircraft. The coverage is divided into 7 12-degree sectors, which provide the basis for determining the direction of arrival of a signal. Now we'll follow a single pulse diagrammatically. Here is the antenna assembly that receives the pulse. It is divided into 2 identical antennas connected by a waveguide and includes an interferometer. Due to the direction of arrival of this pulse, it reaches one antenna before the other. The time delay from when the first antenna picks up the pulse to when the second antenna picks it up establishes a position of null in the interferometer. The position of the null varies the strength of the pulses along 4 probes from the interferometer to the direction mixer. This variation in pulse strength tells the direction from which the signal arrived. Also into the direction mixer goes a pulse that tells it the signal arrived on the left side of the aircraft. The direction mixer converts pulses from all antennas to a compatible form and outputs the directional pulses to the directional encoder. The encoder translates the pulses into digital language, and they come out as a direction of arrival signal in the form of 4 digital bits of information. 1 bit to indicate left side, and a 3-bit binary number giving the sector in which the signal arrived. Also from the antenna assembly, a pulse has gone to the frequency mixer. This unit converts the pulse to an intermediate frequency and forwards the signal to the coarse frequency encoder, which is part of the frequency encoder. Here it is put into digital form, coming out as a 4-bit binary number representing coarse frequency or receiver band number. Simultaneously, the pulse goes to another unit called the pulse analyzer, which measures pulse width and converts the measurement to a 4-bit binary number. The analyzer also measures relative pulse amplitude and expresses it as a 4-bit binary number. While the pulse is being analyzed, it is also being sent to a coded pulse detector, which puts out a 1-bit signal called the CPD alarm signal that says whether or not this is a coded pulse. All the information, coarse frequency, pulse width, relative pulse amplitude, CPD alarm, and direction of arrival, feed together into the digital data output unit. This unit's output is the nearly complete ECM word, lacking only time of arrival. The word is sent to the programmer and put in temporary storage registers. The programmer has a digital clock driven by a 1 megacycle oscillator and receives from the coarse frequency encoder an instruction signal to read time of arrival. It adds this information as 10 bits from the clock to the nearly complete ECM word in the temporary storage registers. Then the complete ECM word goes to the write gates. Through the gates, the programmer controls the priority for the release of the ECM word to the magnetic tape. This avoids interference with data from other sources that must go on the tape periodically. The tape has 16 tracks, each assigned to carry particular categories of information. Under the priority system, the ECM words are recorded continuously, except when other information of a higher priority is being put on the tape. In addition to the ECM data, a variety of other information is continuously streaming into the programmer. From the flight digital data system, the inertial navigator, the BN computer, the radar altimeter, and the air data computer, flight data flows to the programmer digital data system, which processes it into a navigation word and a supplementary word. It also supplies a fixed data word. The shaft encoder provides a frequency insert word, and the digital clock feeds a time insert word and time markers. A system status word comes from control box settings. Using the right gates, the programmer puts the various words on the tape according to its priority system. All these other words make it possible for the ground system to interpret the emitter signals and put them to use. We have traced the passage of one pulse from just one emitter onto the tape. The tape, of course, contains the data from many pulses from that emitter and many other emitters. The system is capable of recording 7,000 pulses per second, along with all the other data that flows to it throughout the flight. Even though all the bits of data are placed on the tape in an orderly manner, they now have to be sorted out and reassembled to make them intelligible. The tape is received in the EDP area. We'll follow the processing to get a general understanding of how the system employs the pulse data we have seen put on the tape and data from other pulses from the same emitter to provide the electronic evaluator with useful intelligence about the emitter, where it is located, and the kind of emitter it is. The first thing that has to be done is cut the tape in half. Due to its length, a full tape must be processed in two separate sections. The airborne tape is mounted on the magnetic tape processor and made ready for reduction, as processing is called. Let's look at a diagram of the overall processing system. We can think of the Q20 as being at the center of things. It has a two-way channel to the magnetic tape processor, in which the airborne tape is mounted, and to each of the magnetic tape units, or MTUs. It is also in two-way communication with the EDP teletypewriter. Also included in the system is a paper tape unit. Located in the EDP area, this unit is used as a high-speed input and output device for the computer. The Q20 likewise has an input channel from the electronic evaluator's program request panel, a two-way connection with his teletypewriter, and an output channel to the station's digital plotter. The evaluator sets up for the area activity program, gives the computer the geographic coordinates of the area boundaries, and stands by to receive information. Through teletype to computer communication, the Q20 requests proper mounting of scan word and airborne tapes and receives confirmation from the EDP operator. When the EDP operator tells the computer the tapes are mounted and ready, processing starts. It consists essentially of sorting scans from the same emitter and is carried out in 3 steps. In the first step, the building of the scan word tape, the computer searches the airborne tape for emitter signals that originated in the defined area. Then it sorts this ECM data according to radio frequency and pulse frequency and puts the sorted data on the scan tape. It also transfers pertinent navigation information. When the airborne tape is completely processed and the computer has completed the scan tape, it informs the EDP operator and tells him to mount another tape on another magnetic tape unit. He labels this the emitter word tape. Again, he gives the word to the computer that the tape is mounted. This is step 2, the processing of the data on the scan word tape to form the emitter word tape. In this step, the computer processes the scan word data to bring together the pulses from a particular emitter in one scan with the pulses from the same emitter in each successive scan. The computer does this for every emitter detected by the aircraft in the designated area and puts the sorted data for each emitter on the emitter word tape. The appropriate navigation information is also transferred. During this time, the computer also sends to the electronic evaluator a running summary of the information that is being decoded by the processing. His teletype gives him a readout of how many emitters have been processed. From the data provided to it, the emitter word tape carries information as to how many times each emitter was intercepted, the direction of arrival of each intercept, the position and heading of the aircraft at each intercept. With this information, step 3 is possible. That is, the processing of the final data tape, which has now been mounted on another MTU. Step 3 involves reading information recorded on the emitter word tape back into the Q20, which utilizes it to determine the location of the intercepted emitters. Having a series of positions and headings of the aircraft and the direction of arrival of each intercept, it is a simple mathematical task for the computer to determine the location of the emitter. The computer transfers this information to the final data tape. This tape consists of data on emitter locations and emitter characteristics. It may be utilized as a permanent record of the mission. When the final data tape is rewound, the program is ready to provide the requested outputs. The computer reads the data taken off the tape and gives it to the teletypewriter and the digital plotter in the electronic evaluator station. In the hard copy printout, it gives them a complete rundown on each emitter. The printout translates like this. Signal number 2, picked up in band 8 on right side of aircraft. Located at 2224.4 north and 8007.5 west. Frequency 2,615 megacycles, 1 megacycle variation. Pulse repetition frequency 375. 0.07% deviation. Pulse width 2.5 to 3.0 microseconds. 17 scan words. The ellipse size has semi-major and semi-minor axes of 6.4 and 1.6 nautical miles and is oriented 199 degrees true. This signal was picked up in Sector 2 and lost in 7. The closest point of approach between the aircraft track and the emitter is 61.9 nautical miles. The signal was first heard at 1623 and 54.1 seconds and was held for a total of 7 minutes and 32 seconds. The relative power amplitude of the signal was 2. On the plotter, each emitter is plotted at its geographical location and each point is given a symbol showing its type. Ground control intercept, early warning, missile control, coastal surveillance, or as in this case, unknown. For each emitter, the printout also gives the evaluator all radars that match the parameters to help identify it as precisely as possible. The computer may further identify the emitter, matching this data in a comparison with data on an electronic order of battle tape. This is called an EOB match. All significant data will be taken by the electronic evaluator to photo intelligence operators for evaluation and updating mission folders. This rapid correlation of non-image and image data is one of the most valuable features of the IOIS. Now that the processing of the final data tape, printout, and plot is completed, the pertinent intelligence derived from the tape is disseminated in various ways. Printouts and plots may go to personnel aboard ship. Message reports may go to other units in the area. Punched paper tape may go to ELAN centers for additional analysis. And SNR forms are filled in, so information may be incorporated in the database. The tape itself may be stored for future use aboard ship. In these days of electronic warfare, the great value of the RA-5C's passive ECM system is that it can automatically record all electronic pulse emitters received by its antennas while flying over an objective area. Then, on returning to the carrier, this recorded data can be quickly decoded in the IOIC so that the electronic environment of the objective area can be reconstructed. This reconstruction of the electronic environment helps immeasurably in selecting and assigning targets, planning tactics, and scheduling the mix of strike mission aircraft and the fuel, ordnance, and electronic warfare loading of each for the attack.